A speaker tonight. It's a gentleman named Vincent Ledvina. You might be aware of him. He has a large online presence where he's known as the Aurora guy. He's also currently a Ph.D. student in astrophysics as well. So he does classes by day and auroras by night, I guess. So anyway, he has about 36,000 followers, for example, on X right now. So he's very, very popular. Anyway, I'm assuming he can hear me. He's in the meeting now. Yep. And take it away. We could hear you. You just said yes.
Right.
And we could,
yes, I did.
We could see your display on our whiteboard. So take it away. I'm going to let you have it now.
All right. Sounds good. Yeah. Thank you for having me. Really stoked to be here and to speak to all of you. My name is Vincent Ledvina, and I'll be talking about chasing the Aurora, nature's most spectacular light show. So we can take questions at the very end. I have about a 40-minute presentation, and that'll leave us roughly 10 minutes for questions, and we can spill over if we need to. So let's take it away. So here's a quick outline of my talk. I'll first go into who exactly I am because, I guess if you follow me, then you probably already know. But if you don't, I'll just share a little bit about my story and how I came to chase the Aurora, and then I'll delve right into the science of space weather and auroras. When the sun gets angry, so when space weather rears its head, and you could potentially get aurora down in Arizona. We'll talk a little bit about forecasting the aurora, some chasing tips and tricks, photography, time-lapse, real-time video, and if there's time, I'll show you some of my favorite aurora photos. So a little bit about myself. Like was said, some people call me the Aurora guy. It's a name that I got when I was actually at the University of North Dakota doing my bachelor's in physics. So I moved to North Dakota. I'm originally from the Twin Cities in Minnesota. So I've only been in Alaska for 3 years, actually, but I love it here. And yeah, I guess I just got this name, the Aurora guy, out of chance. I started sharing my photography on social media, and that was just the name that was given to me. And at first I was, a little bit shy about promoting that, but people said, no, this is just what you do. So you should just, take it and run with it. So that's what I'm going to do. And I live in North Pole, Alaska. And I say that because it's just kind of a cool name. And whenever I travel outside the country, people always think that I have a fake passport because it says I live in North Pole. And apparently they don't believe that, that's a real thing. So being in Alaska, I moved here to go to school. So I'm doing a space physics Ph.D. program. So space physics is kind of like astrophysics, but it's everything inside the solar system. So really it's everything that you don't see and that most people don't care about, which is all the stuff in between the planets, all the space plasmas. So that's what I'm studying. And that also includes the aurora, things like the ionosphere, the thermosphere, the exosphere, all the different spheres, heliosphere. So I have about 3 years left in that program. I'm a professional aurora chaser. I run tours and workshops and all that in my free time. I'm an intern, so kind of at your latitude, down in Los Angeles at the Aerospace Corporation, so I'll be back down there again this summer. And I'm really passionate about citizen science and science communication. So here are just some quick slides, aurora chasing adventures through the years. This was back in 2022. I went to Churchill, Manitoba, which is on the southern shores of the Hudson Bay, and spent a week up there aurora chasing with some friends. And it's a very different kind of experience, aurora chasing up in Churchill, because you have to worry about these guys here on the left, these things called polar bears, which are a little bit more unfriendly than the bears that you're maybe used to, black bears and brown bears. And we saw a bunch of them when I went back in September, a little bit too close for comfort in some instances, especially the one on the left there. That was actually just, we had just enough time to grab the camera, but we almost actually hit that polar bear. It was in the road as we were turning a corner. And the one on the right was one that we actually saw as we were changing locations from one place to another. So, when you're out aurora chasing in Churchill, you kind of scan the horizon as you're driving. Somebody sticks their head out the sunroof and, with this spotlight kind of scans the tree line to make sure you don't see any eyes. And we thought we were good. And then, of course, the moment that we left, polar bear was in the road. And we were like, wow, that was a little scary that we didn't even see that thing. So, but in Alaska, the auroras are amazing, far different than maybe what you're used to at mid-latitudes in Arizona, or even if you've, been to other states like Minnesota or Wisconsin. In Alaska, in Fairbanks, the aurora is right overhead, and we get it every single night as long as it's clear and dark. So, right now it's April 18th. So I'm actually in Anchorage right now. I'm just here for the weekend, but the sun doesn't set until about 9:40 p.m. and it rises at like 6:30. So we've already lost our full night, and we're going to be losing our astronomical twilight in about a week. So it's impossible to see the auroras after about 2 weeks. In Fairbanks, even at the dead of night, it's just not dark enough. So aurora season is really from the end of August until the end of April. But here are just some, little snapshots of, this is actually my first big, really big auroral display I ever saw, which was in Fort Yukon, Alaska in 2022. This is actually before I moved up to Fairbanks, and this is what drove me to pursue my PhD at University of Alaska Fairbanks, because I thought to myself, if I'm going to study this thing for potentially 5 or 6 or 7 years, I want to, at least see it, at least like see it once in a while. I don't just want to be doing these equations and homework without having any kind of ground truth. So this is a real-time video on the left, and then a still image. I'll just go back to the big spiral, a still image of that video on the right. Okay, so that's a little bit about myself. Now let's delve into the science. So space weather, what is space weather? Well, the technical definition is that it refers to conditions around a star like our sun and its interplanetary space that may affect space and ground-based assets as well as human life. But when I tell people what space weather is, I just like to say it's the aurora, because it sort of represents that final step, all the energy from the sun eventually getting to the earth and causing this beautiful light show that we see and that we can enjoy. But it's not just the aurora, obviously. There's so much more going on under the hood. You have shock waves in space, million-degree plasmas on the sun and the sun's atmosphere. You have really cool space missions that are super inspiring, like the Parker Solar Probe, giant explosions, CMEs and solar flares, billions of times stronger than any bombs that humans have ever created. It's just a really exciting field that, unfortunately, people just, I don't think know too much about. It doesn't really get the same press as, James Webb Space Telescope or, Hubble imagery, but the aurora is pretty amazing. And when you really get into why it occurs, you start to learn that there's a lot going on in outer space and with the sun that you may have not heard of before. So it all starts with the sun. Like we have weather here on Earth, there's clouds, rain, wind, and storms. On Earth, the sun creates weather in space, and there are similar analogs in space weather that there are to Earth weather. So the sun gives us warmth and life. It might be 105 degrees in Phoenix or something, and you look up and you're, shaking your fist at the sun, like, why are you doing this to me? But it's the reason why we're all here. And, besides just being kind of an ever-present, fixture of our lives, right? I mean, it's there all the time. Our lives revolve around the sun. We wake up and we go to bed with the sun. It also gives us space weather. So the sun, even though it seems like it's just this sort of static ball of light in the sky, it's dynamic and constantly changing every minute, hour, and day. And this is what gives us the concept of weather. There's this wind that blows out from the sun called the solar wind. And usually it's calm and gentle, but sometimes it can become really strong and fierce. You have coronal mass ejections, which are big explosions of plasma on the sun and high-speed streams of solar wind from coronal holes. Those are those gusts and those fast solar wind streams. And the actual wind itself carries charged particles and magnetic fields, which bathe the entire solar system in this energy. And that energy can interact with other magnetic fields like those around planets. And Earth has its own global magnetic field, which extends out into outer space, which I'll show you in a little bit, called the magnetosphere. And that interaction between the solar wind and Earth's magnetosphere is how the sun touches all of us and eventually creates the aurora. So let's see if this movie plays. This is just a little kind of highlight reel. I could watch these kinds of videos for hours of different processes on the sun, just showing you that there's a lot going on that you may not be aware of. So you can't see this stuff from the ground because these images are all taken in the ultraviolet. So Earth's atmosphere, thankfully, otherwise we would all be burning up and have skin cancer at this point probably. Earth's atmosphere blocks all this ultraviolet radiation, but if we're in space, we can put special filters on cameras and image the sun's atmosphere called the corona. So you've probably seen a total solar eclipse, or at least a photo of it. That corona is kind of the birthplace of the solar wind, and that's what we're looking at here. And you can see all these different things, these huge loops of magnetic fields. You have these explosions and bright flashes, solar flares. These are active regions. So sunspots you actually can observe from the ground with a solar filter and a big telescope. But These are sort of the magnetic signatures in the sun's atmosphere. Seen here, there's a solar flare, and it looks like a CME launching off right there. There's a big prominence eruption. So, this stuff happens all the time. We just had a big geomagnetic storm a couple days ago, KP8. So, that's a G4 out of a G5. So, I mean, that was a pretty big event caused by one of these CME eruptions. These things happen all the time. This is a 4-minute highlight reel, but you could fill hours with these explosions. So all this energy goes out into outer space, and then what happens? Well, it'll just flow out basically forever until it eventually loses its pressure and reaches a sort of equilibrium with, what's beyond the solar system. And it forms this huge sphere called the heliosphere, sort of protective bubble around the entire solar system. But planets themselves, if they have a dynamo in their core, create a magnetic field which then extends out into outer space. And our Earth is one of these planets. And our Earth, this protective magnetic shield is called the magnetosphere. It's kind of like a rock in a stream of water. The solar wind flows past and pushes against the day side of Earth's magnetosphere, compressing it. And then the night side gets extended out, kind of like a comet's tail. And when the solar wind hits this bubble, depending on the strength of the wind, some of the particles, those charged particles, which are riding along those magnetic field lines, can get funneled into Earth's magnetosphere, so kind of hands off that energy and over the polar regions, which is why we get auroras over the north and south poles. And auroras are created in a layer of the atmosphere called the ionosphere. It's one of the highest layers, many times higher than a plane flies, so 15 to 50 times higher. That's around 150 to 500 kilometers in altitude. So whenever someone goes to Iceland or Alaska, and they say, well, I should be able to see the auroras every single night. I say, well, it has to be clear. And I think that's something that has to be said, because a lot of people think, oh, I can see them because they're just like clouds, right? No, they may look like clouds, but they're way, way, way higher than the clouds that we're used to. So the ionosphere itself is sort of where the gas that we breathe, we're used to N2 and O2. In those upper layers of the atmosphere, it gets so tenuous or less dense that those molecules can break apart into their sort of atomic species like O plus and N2 plus. And that's why we call it the ionosphere, because there's charged particles, and I guess that's considered plasma, just flowing around up there freely. So these charged particles from the solar wind that are riding along magnetic field lines, those get sort of catapulted into Earth's magnetosphere. So now they're in Earth's magnetosphere. They're also flowing along Earth's magnetic field lines. And those field lines kind of converge over the poles. So now you have all these particles rushing in. They're about to slam into Earth's atmosphere. And the first things that they encounter are these, atomic oxygen species around, 500 to 1,000 kilometers in altitude. As you go further down, if you're kind of building this auroral arc from the top down, the gas just gets more and more dense. So if you're a charged particle, you have a certain amount of energy. Let's call it 1,000 electron volts, right? As you go down from outer space into Earth's atmosphere, you start encountering more and more dense gas. And when you're colliding with these gas molecules on the way down, you're donating some of your energy to them. And those chemical reactions produce light in specific colors. So, if you encounter an atomic oxygen particle at, 120 miles way up in the atmosphere, that's only a 5 EV reaction. So, as you're moving down, it's kind of like a game of Plinko. You're just hitting all these gas molecules on the way down until you get to a layer that's too dense, where you just give up all your energy in a short amount of time. So if you have more energy, if you're kind of the point of view of the electron, if you have more energy, you're coming down and you're being able to penetrate further into the atmosphere. You're able to interact with different species of gas and produce different colors. So red auroras caused by atomic oxygen being struck by an electron. And then you have this green emission, which is the most common and also the brightest, which is kind of a two-step reaction between nitrogen and oxygen. And then if you have a lot of energy, you're able to make it down to this layer of N2, which is actually the stuff that we breathe. And that's really below 60 miles. And if you have a lot of energy, you're able to excite those molecules and emit sort of a whitish, pinkish light. So that's sort of the precipitation. If you think about the terrestrial weather and the rain that we have on Earth, in the upper atmosphere and with the aurora, you have a rain of electrons coming in from outer space, which we call particle precipitation. And the clouds in outer space, that produce these raining flows of electrons, are kind of like the clouds that we have here on Earth producing the rain that we feel on the ground. So everything that you see with the aurora, it was really created somewhere in the magnetosphere. So that's why scientists like to study it, is because when you look up and you see the aurora, if you see a big swirl in the aurora, that actually corresponds to something happening in outer space to create, that shower of electrons that makes it down to the atmosphere. So everything's connected. And I like to say to people, if all this sounds confusing, really the aurora is just like a giant neon lamp in the sky, except for the electricity comes from outer space instead of the wall. And here are just some rare auroral colors. And, I just said that you just get, blue, green, red, and maybe a whitish pink. Well, those altitudinal ranges where those emissions happen aren't just hard cutoffs. There's some overlap. And also auroras are really in 3 dimensions, but you see them in 2 dimensions, right? You're just looking at a plane in the sky. So things can overlap. So you can get green overlapping with red, which can create yellow and orange. If you have really low energy precipitation, like the one here on the left, those particles, none of them will really get to that green layer. So you only have this sort of pinkish, bluish aurora. And there's a little quirk too. If you have aurora really close to when the sun sets, the sun setting, it still is shining in the upper part of the atmosphere. So even though it's dark on the ground, the sunlight is still striking these molecules up here in the ionosphere. So that sunlight can actually ionize N2+ and create blue emission, which can then mix with the red and create pinks and purples and things like that. Here's another example of that on the right. This was March 23rd, 2023. So almost 2 years ago, we had a really big geomagnetic storm and had aurora right away after sunset and got some amazing colors. So these are just some nice photos I have showing that the aurora is not just green. I think a lot of people think that too, that the aurora is just a green, blob, doesn't really move at all. And once you've seen it, you've seen it. But I can tell you for sure that that's not how it is. And so going to this concept of the auroral ovals, here in Fairbanks, or I guess Alaska, I'm in Anchorage right now. So technically right now I'm a little bit south of the northern auroral oval, but in Fairbanks, we're right underneath that auroral oval. And this is what happens when you just have sort of, the actual reasoning behind why they're ovals and not just like little patches is somewhat complicated, but it has to do with the fact that the geomagnetic and the geographic poles are slightly offset. That just creates these donut shapes of constant auroral energy that persist even when the solar wind is really quiet. So if you travel to underneath one of these auroral ovals, it's going to be a little bit hard to get to Antarctica, but if you go to somewhere like Fairbanks or Iceland or Tromsø in Norway, as long as it's clear and dark, you have a 100% chance of seeing the aurora in some capacity. Okay, let's go over auroral substorms. So a lot of this might have been review if you're into Northern Lights or into aurora, but substorms I haven't seen a whole lot of talk about, but they're really fundamental to how the aurora works. So over the course of a night, maybe you just have some steady state aurora. If you have, a little blip in the solar wind, some stronger magnetic field, you can cause this substorm sequence to start, where you have a charging up of the auroral ovals over time, which can last, anywhere from 2 to 3 hours. It's when all this energy gets built up, and then all of a sudden that can be released in what's called substorm onset and expansion. And you can see here on the right, this is an all-sky camera time lapse from Fairbanks, showing just kind of, normal aurora. And then all of a sudden, once I press play, you'll see it, it just explodes all across the sky, but it only lasts like 15 to 20 minutes. That's the auroral substorm. It's the sudden release of energy in Earth's magnetosphere that then manifests in the ionosphere as aurora. So remember I said, we study the aurora. The whole purpose of studying the aurora is to figure out what's going on in Earth's magnetosphere. So when you have, it's sort of like a bucket of water slowly filling up, and then someone comes over and kicks it over and all the water spills out. Imagine all that water is all these electrons being dumped into the atmosphere. Or another analogy that I use is a big rubber band, full of, if you're ever, if you were one of those kids in class, you would, shoot little paper balls through rubber bands at people. Imagine that paper ball is a big ball of auroral particles. Well, over time in that growth phase, that rubber band stretches out, and those particles are, increasing in potential energy. Then all of a sudden that rubber band lets go, those field lines snap back, and all those particles get slingshotted back to Earth's night side and enter the atmosphere and create this huge explosion of aurora. And this is really crucial, because this kind of determines if you can figure out what phase of the substorm you're in, and whether you're in a growth phase or also after one of these big explosions of aurora. You usually have a 1 to 2 hour kind of cooling down period called the recovery period. If you can figure out kind of where you are, if you are in one of these substorm patterns, you know whether to stay out or whether you should pack it up. And that's really important. And also for people who are chasing the aurora at mid-latitudes, if you have a substorm, in the auroral oval, let's say that things aren't really that, enhanced, like there's not a big geomagnetic storm, even though there might not be a huge geomagnetic storm, when that substorm happens, you have so many more particles, and I'll show you examples of this, but the entire aurora just becomes brighter, including the very tops of the aurora, which are really high in altitude, like 500 kilometers. Just like you can see a storm really, really far away on the horizon because it's so tall, if you have aurora that becomes really, really tall and really, really bright, well, now all of a sudden people further away from the auroral oval can see that. Even though the curvature of the Earth will block the lower green parts, you can still see the red. So that's how you can see aurora. Aurora was seen on the very border of northern Arizona 2 nights ago because of one of these huge substorms. So this is really important because not only does it apply for high latitudes, it happens every single night, 1 to 2 times a night, but during geomagnetic storms, when the auroral oval is a little bit further south than usual, one of these substorms can kick things up and cause you to see aurora only for brief periods, maybe 15 to 30 minutes, from really low latitude places like Arizona, California, Utah, New Mexico, places like that. So yeah, I just kind of mentioned this, but what causes the aurora to be seen at mid-latitudes? Because even though you have a substorm, it doesn't mean that you're going to see the aurora every single night in Arizona. But that's when the sun gets angry. So usually the solar wind's sort of flowing at this steady state, but we can get big gusts of solar wind called coronal mass ejections, which are like sun sneezes, and those launch bits of the sun's atmosphere, chunks of plasma into outer space. And if they're directed at Earth, they could take 1 to 3 days to reach us. So they travel pretty fast. And when they hit us, it's just a huge gust of solar wind. So we have more energy, more particles, higher magnetic field, and that can cause a geomagnetic storm where the auroral oval is actually pushed to lower latitudes. And it's really hard to predict these solar storms. We have the NOAA Space Weather Prediction Center, which is the official space weather forecasting center here in the US. But we also have people like Tamitha Skov, who's one of my friends. And also I do this too, where, we try and, because, a lot of this is really hard. So, I mean, people at NOAA SIPSI, they are the experts, but, it doesn't hurt to have some other opinions, because people say that space weather is like where, terrestrial weather forecasting was in the 1960s. It is really primitive still. So people like Dr. Tamitha Skov, if you want to learn more, she's also a ham radio operator. I need to get my license soon. But she's kind of in this community of amateurs and space weather enthusiasts. She was actually working at Aerospace for a while, so she has the expertise, and she breaks down these space weather forecasts that are outputted by NOAA SWPC for their customers, like power grid operators, the military, people like that. They're not really forecasting the aurora, but social media influencers or social media enthusiasts like myself or Tamitha will kind of take what's being put out by NOAA SIPSI and say, okay, what does this mean for aurora possibilities? Because the NOAA Space Weather Prediction Center, a lot of people don't realize this, they may care about aurora chasers, but they just don't have the bandwidth nor the funding to do that. So, and this year, is a really great time to see the aurora because we're in this period of time called solar maximum. So we may actually be coming down from solar maximum. As you can see here, this is sort of the latest projection by NOAA. You can see maybe the sunspot number has peaked, and the sunspots are kind of a proxy for solar activity in general. So you can see it kind of, well, this only shows one cycle here, or about half a cycle. But if you look here on the bottom, you can see all these different humps. Those are all the different solar cycles throughout time. Going back, it looks like to 1750. So we're in solar cycle 25. And people have been measuring sunspots for hundreds of years. Galileo was one of the first people to notice these sunspots, and every roughly 11 years we go through a solar maximum where we have more sunspots, more active regions, more coronal mass ejections, and more of these geomagnetic storms. But actually solar activity and auroral activity peaks are slightly offset, so we should see the peak of auroral activity about 1 to 2 years after solar max, which is, if we think solar max may have been in 2024, well, maybe we should be seeing the peak of auroral activity this year or next year. So it's not the end of the world. You might see this graph and, be a little pessimistic and a little bit sad, but don't worry, the best is probably still yet to come. So now is a great time to be an aurora chaser. And we can predict the aurora kind of, it's hard, right? Like anything in weather, but space weather especially, it is really hard to predict the aurora because there's just so much that goes into it. And we also just don't have a lot of monitors. We only have, a few monitors in space, and there's just not enough data to really make a good prediction. So a lot of it is reactionary. We'll see something in the solar wind hitting us, and then, in 30 minutes that arrives here at Earth because we have satellites a little bit upstream, able to measure these things and beam back the data at light speed. So we have a little bit of warning, but really beyond like an hour, we really just don't know. It's just best guesses. So most websites will use something called the KP index. That stands for K planetary. I just want to talk about this because a lot of people get obsessed over these KP indices and forecasts and the view lines. But it's kind of problematic because it's a global average of activity every 3 hours. And like I was just saying with the substorms, right, we can have a big intensification of aurora that only lasts 10 or 15 minutes. So that won't get captured in the KP, which is a 3-hour average of global geomagnetic activity. It's like trying to say, in monsoon season, you're trying to figure out when a storm is going to hit your house, and somebody gives you, the number 3, and you say, well, what is that? And they say, oh, it's the global raininess index. And you're like, okay, well, great. How does that help me forecast when this storm is going to hit my house? And the person with the 3 says, well, I don't know. That's like Noah Slipsey giving the aurora chasing community a KP3, and saying, well, I don't know what this means, but here you go. And then the aurora chasers just assume it means, oh, well, we're going to have, whatever kind of aurora. So that's kind of how it works. And a lot of people don't realize that. So just be aware that the KP index is not the be all and end all. What I really prefer are webcams. And of course, these are most relevant for people up at high latitudes like me, and people in Fairbanks or Iceland where we're seeing aurora all the time. So I always have this webcam pulled up. But if you're in Arizona, maybe you do want to wait until a decent KP6, KP7 storm is forecasted, because chances are you're not going to see anything at a KP1 or a 2. It does track at some point. It's kind of like, if the entire stock market is crashing, your stocks are also probably going to crash. But if you're just trying to look at one stock, you can't use the Dow Jones to make a one-to-one correlation to what's going to happen with your pick. So at some point the KP does track, but there are webcams all over the US, and I have a big list on my website where you can tune in and see what's going on. So I always tell people, if you don't want to care about the science, you don't want to care about the KP index or forecasting CMEs, any of that, just go check out the webcams. If there's aurora on that webcam and it's near your location, well, you're going to see the same aurora because the aurora is huge, right? It's occurring high up in the atmosphere, and these structures are hundreds of miles across. So I've been on the phone with people. When I was living in North Dakota, I would be on the phone with people in Duluth, which is a city in Minnesota, about 250 miles east, and we'd be looking at the same auroral pillar and talking about it in real time. So if you see a webcam, and even if it's like the next state over, if it's roughly the same latitude as you can use it for detecting aurora. We also have lots of other tools like the Ovation Prime model. This one's kind of nice because it takes what's happening in the solar wind and runs it through a fancy equation, which outputs what the auroral oval should look like. It's a statistical model, so it won't show you when substorms happen, but it will show you in general, if you have better solar wind conditions, you should see a more expanded auroral oval. There are things like the GOES magnetometers, though, that you can use to detect substorms. There's also tools like the ENLO model, which you can use to forecast CMEs, and the auroral electrojet index, which is kind of like the KP. If you just want something that says higher number equals better, the AE index can help with that. Forecasting solar wind, since we're probably looking for CMEs, if you want to see aurora in Arizona, you need some sort of geomagnetic storm to see aurora. You can get a nice substorm at a KP5 or a 6, but that's still a KP5 or a 6, which will require some sort of enhancement in the solar wind that doesn't just happen randomly. Usually have to have a CME to create something like that. So there's a model called the ENLO model, which is used by all the forecasting agencies. It shows the solar wind profile and the model of that from different views, like a top-down view and a side view. There's also this HUXT model, or people like to say HUXT, which is, uses the ENLO model, but outputs the sort of, arrival times of these CMEs and sort of the different parameters in a slightly more user-friendly way, even though this looks like a, kind of eye chart. I actually think this is nicer because it shows you the uncertainty in the models, which is really important. If you see a CME is forecasted, let's say on, April 26th at 12 UT, that might give you some confidence that, oh yeah, those forecasters really know at 12 UT the CME is going to hit. But in reality, these forecasts are plus or minus 7 hours. And, a lot of times, if you see these things posted on the SWPC website, or, local meteorologist is saying that the quote unquote space weather forecasters are predicting an impact tonight, that doesn't really tell you what the CME looked like, if it's a grazing blow, if it's a direct hit, what the uncertainties might be. So this site, the Huxty model, is really good for that. We already talked about the KP index. Here are actually where the observatories are that measure the magnetic perturbations in the ground that go into calculating the KP index. So you can see that, they're all over the world, and, a lot of them are also in Europe too. So like if you have a localized aurora, let's say over Greenland, for example, there's no station there to measure that. So actually that'll just get completely ignored by the KP index. And so a lot of things rely on the KP index. This is my favorite thing, the Chena Hot Springs whiteboard near Fairbanks. They actually just got rid of the whole idea of KP, and now they just say the Aurora Activity Index, which I think is even worse because you can't even look that up. I mean, if you're a tourist and you're like, well, what is this KP index? At least you can maybe at some point figure out that it's not the best thing to use. But now it's just, how active is the Aurora? It's a 3 out of 9. Okay, great. People think, oh, wow, it's a 3 out of 9. That's horrible. And then they don't even go outside. But actually a 3 is pretty good. So that's just funny. But, the SWPC website, NOAA SWPC, puts out forecasts for the KP over 3 days. Those are just like throwing darts at a board, honestly. I wouldn't pay too much attention to that. But if you see like a KP 7 or 8 in the forecast, I mean, okay, somebody at SWPC thinks something is going to happen. So then it's worth paying attention to. But if you see like a 2 and a 3 and a 5 and a 4 and a 1 and a 2, I mean, yeah, just, shuffle that up and that's just as good as the last one. The KP index also gets baked into a lot of apps. If you have an Aurora app, you probably have the KP in there somewhere. Then, of course, the news is great at picking up on these solar storms and making their own view lines with, very hard boundaries. Like, oh, if it's a KP6, you should only be able to see it from this little band, which is not true at all. Substorms can push the Aurora and the visibility of the Aurora down to much lower latitudes for a short amount of times, even with the KP being, maybe 5 or a 6. The Aurora oval might be resting above Canada, but if that substorm is really big, you could see that Aurora all the way in, let's say, Colorado or Utah. So you don't need a KP9 to see the Aurora in those more lower latitude states. So we already talked about this. Let's just quickly go over the AE index. It's kind of like the KP index, where a higher number equals better, but it uses high latitude stations. So this is really helpful if you're in somewhere like Fairbanks, where you're actually at high latitudes and you want an index that matters for you. But it does track for mid latitudes as well. So, for you in Arizona, you might want to look for values over 1,000 to where you might want to start paying attention. And these track pretty well with substorms, although it's delayed a little bit. Real-time solar wind is helpful, obviously, because it gives you all the information you need relatively. And you can see, it's measured in, well, I should back up here and say that we talk about the magnetic field as the letter B, B as in Bravo, and then we have a coordinate system that we define here with a Z and an X and a Y. What matters for Aurora is BZ South, because Earth's magnetic field flows out from the South Pole into space and then down through the North Pole. So if you kind of do that motion with your hands, your arm is physically moving from the bottom to the top. So that direction is BZ North or BZ positive. So if you imagine bringing two bar magnets together that are opposite in polarity, if you have a north, which is always what Earth's magnetic field is, and a south, those two will attract and you can get energy that transfers from the solar wind to Earth. And that's how we get the substorm cycle to start up. And also you can get substorm expansion, which is when the aurora really intensifies by when the BZ turns, it's called a turn, from south to north. And so I have this whole ebook. If this is all confusing and you need some reading material, I'll have this QR code later, but I got this ebook that's free, actually. It's like 60 pages. I just wrote it during my winter break, and it's got a bunch of information on how to look at the solar wind, but that's an entire hour-long presentation in and of itself, so I'll just be kind of glossing over that. If you don't want to read the solar wind, the Ovation Prime model, like I said, just kind of bakes in all the solar wind, puts it through a fancy equation, and you get a nice auroral oval, which also tells you the quote-unquote power of that aurora in gigawatts. So yeah, there's a lot of power in the aurora actually. Hundreds of gigawatts. I think there was actually a mission. I don't know when it was, probably 30 years ago, that tried to fly a little like EMF generator through the aurora to see if the U.S. could harness power from the aurora, but that didn't quite work out. But if we could power the country for days or weeks with just 10 or 20 minutes of aurora. There's a lot of power up there. So this is kind of a really friendly model, but again, it's just a statistical model, so it's not actually showing you where the aurora is, just sort of where the likelihood of seeing the aurora would be. And also remember that during substorms, which are not captured by this model, you could see aurora further south. All right, so forecasting auroral substorms, you can use a lot of different tools. One thing that I like to use is this GOES magnetometer, and you just look for these spikes in the graph. Those correspond to when the rubber band is releasing, and you have a huge flow of particles from the magnetotail to the night side, causing this big intensification in the aurora. I'm going to kind of go a little bit quicker here because I know that we're already at quarter two. But, okay, yeah, the best sort of data set that you can have is ground truth data, right? You can have all these fancy graphs, equations, and that's you guys. So there's sites like Aurorasaurus where you can actually report if you've seen the aurora or not, and those get put onto a map, and you can track that over time and see where people are physically seeing the aurora and have made a positive report. And there are webcams as well, like I was saying. This is just kind of a cool example of using webcams to figure out where the auroral oval is in real time. This was during the October 10th storm in 2024. Maybe you all saw that down in Arizona. I think there was actually some nice SAR arc activity from down there, but you can see here a camera in Maine showing the aurora to the south and a camera in Georgia showing the aurora overhead and to the north. So somewhere in between is where the auroral oval was resting. And there's multiple different time scales on which you can do forecasting, hours to minutes to days. It gets less accurate as you go out in time. And so here's sort of my aurora chasing workflow. At high latitudes, I have to figure out if it's cloudy, if it's dark enough, and then I just kind of try and forecast those substorms. And it's the same at mid latitudes, except for you're waiting for some sort of CME activity, some sort of CME impact or enhancement in the solar wind to get that auroral oval just a little bit further south. And so, yeah, this is what I was talking about, a big SAR arc, the stable auroral red arc. Actually, it's a really rare type of subauroral phenomenon, so it actually forms south of the auroral oval. This was photographed in Arizona just in October. All right, so let's blast through some aurora chasing tips and tricks. All you need is a love for the night sky and some patience. People have been talking about the Bortle scale all night. You are all familiar with this, so I don't need to tell you, but you want dark skies to see the aurora. It's going to look very different depending on where you're at. I mean, if you're in Arizona, you're probably not going to see a big auroral spiral like this. This is kind of exclusive to the high latitude locations, but one tip I have is if you don't know what it is, just take out your smartphone and take a quick test shot. You might be able to see something with your phone. And red aurora glow is really common from lower latitudes because you're actually seeing the red tops of the aurora from further away. You're not able to see the green because the Earth is sort of blocking that from your view. The Earth is round, of course, and you're not able to see the very green bottoms of the aurora, even when they're there because the Earth is blocking it. So this is just an example. During a substorm, I was actually in India last year in May during the largest geomagnetic storm that we've had in 20 years. And I saw the aurora pretty close to the China-India border because a big substorm pushed the aurora really high, and I was able to see that from my perspective. And of course, the auroras will not look the exact same on your cameras as they will with your eyes. Things will be a little bit more muted with your eyes than on the cameras. There's tons of variables that affect this, but I will say just that, eyes and cameras work differently. We have rods and cones, cameras have pixels. And so below a certain light level, our eyes just cannot see color, and that's just how it is. But you can also kind of biohack the aurora, and I'll have you look at this down here at the bottom left. If you cannot see the green, I won't tell you what it is, but if you can't see the green in this circle, you have a little bit of color blindness, which could actually affect your ability to see the aurora. A lot of people don't realize it. I've actually had a couple friends come to me and say, yeah, I've just never seen the green in the aurora. I just don't know. And I'll show them, a color blindness test like this, and they say, am I supposed to see something there? And I'm like, yeah, buddy, you got some color blindness. That's probably why you can't see the greens. So if you can't see the green in the aurora, it could be for a lot of reasons, but your cones, which see color, need a little bit of light to activate. And you can actually, it'll ruin your night vision, but shine a flashlight in your eyes, and that causes the cones to activate for about 10 seconds. You can just look away from the flashlight, look up at the aurora, you'll be able to see the greens just fine. So now aurora photography, really anything can do it nowadays. If you have a night mode on your phone, that's good enough. But for DSLR mirrorless cameras, 5 to 10 seconds, lowest F number, ISO 16 to 6400, and shooting manual mode is the best way of doing things. Auroras are hard to photograph, right? For astrophotography, Milky Way photography, it's pretty, I don't want to say easy, but you more or less choose your shutter speed and it never changes. But with auroras, it's constantly changing in brightness. It'll just get really, really bright during a substorm, so you're going to have to respond. And I always tell people to adjust the shutter speed versus anything else. You want your aperture as wide as possible all the time. And this is just an example of how bright the aurora can be. This is 1.6 seconds at ISO 640 on my Sony A7 Mark IV, 14 millimeter f1 or 20 millimeter f1.8 lens. I'm going to skip the little time lapse video, but time lapse photography is a really good way to just set your camera up and take a bunch of shots. And you can capture everything. You don't have to worry about, missing the show if you set your settings right. And to set your settings right, what you really want to do is underexpose a little bit when you're setting up your camera so that you can account for any brightenings in the aurora from a substorm. And I have this blog article on my site, or you can ask me after the talk if you want to learn more about this, but just some general settings too. You want to have your shutter speed a little bit quicker than usual. I tend to use auto ISO. Actually, in newer cameras, this works fine. People are, rightfully afraid of auto ISO because back in the day, the meters inside cameras were not that good. But nowadays, they're great. And I usually try and get 240 photos at least if I'm playing this back at 24 frames per second. So I have a 10-second total movie length. And so here's my editing workflow. I was listening to the talk about AI. I am using the AI denoise in Lightroom now in my processing. So that's what I have down here. There's also this neat video plugin that I don't know if it uses AI or it's just some fancy algorithm, but it may have been updated to include an AI algorithm, but that also further removes noise as well. So I use a combination of LR timelapse, which is actually a free software. It allows you to process up to 400 shots, and then that links up with Adobe Lightroom Classic, and then you can use Adobe After Effects, Final Cut, any sort of processing software to take a JPEG sequence and turn that into a movie, but I just use After Effects, that's what I'm used to. And what I've been really doing recently, if you follow me on Instagram or anything else, I mainly just post real-time videos because it's super easy for me to, take out my Sony A7S III and just, go outside and start recording. And I really recommend investing in a really nice lens because that matters the most when you're trying to get as much light as possible into your camera. And the Sony A7S III is still the king of real-time video. It's 12 megapixels and it's a full-frame sensor, so those pixels are huge. Just some kind of more, about the sort of more nuances about real-time video. I underexpose a little bit. The ISO is going to be crazy. You're probably looking at this and saying, what the heck? But yeah, 128,000 for the ISO. I will be up there when it's a new moon and there's not much aurora in the sky. It is just really, really dark. And I can still shoot video and get relatively clean shots after I've cleaned it up with neat video and After Effects at ISO 128,000. But it does help to have a full moon. So if you're trying to go to Alaska or somewhere else and you want to take a real-time video with the camera that you have, most cameras can do it as long as there's a full moon and the aurora is really bright. But if you do want to get really crispy, clean video, you'll want to invest in a few cameras that are specialized for these low light situations. All right, I don't really have time for show and tell, so I'll just breeze through this really, really quick because I want to be able to have questions after. There's this, it's not technically an aurora, but it's called Strong Thermal Emission Velocity Enhancement, or STEVE, that I photographed in North Dakota in 2021. This was the night that blew me away, March 5th, 2022. So I showed you that auroral spiral that I saw from Fort Yukon, Alaska back in 2022. That kind of inspired me to move to Alaska and go to school. This is that same night. And this is that winter trip to Churchill in 2022, really awesome auroras there. And then again, I went to Churchill. I was taking a gap year, so there's no way I could have done this now with classes and everything going on. But just some fantastic stuff. And then we had this big auroral substorm. So this is what I mean by, things can change in an instant. Boom, right? Just massive, sort of explosion of aurora there. That's what a substorm looks like. And then I need to update this, but I've been shooting mostly real-time videos. So I think these were kind of the last photos I ever took this season. But I think I looked back and I have about 500 gigabytes of real-time video, and those are all like 10 or 20-second clips on my Sony a7S III. I have a folder on my iPhone that just says real-time video, and I checked it today, and I have 2,800 videos in that folder from 2022 onwards. So I see the aurora a lot. I try and go out as much as I can, and it is part of my life, and I guess why people call me the Aurora guy. So thank you for your attention, and I guess we have some time for questions.
Question, Vincent. You mentioned that the aurora cycle is out of phase with the sunspot cycle by a year or so. Is there an
Correct.
easily understandable reason for that?
Yep, it's kind of twofold. So as you go along in the solar cycle, the sunspots start to appear lower in latitude. And if you think about those sunspots as like cannons and those cannonballs as CMEs, as they're moving lower in latitude, so closer to the sun's equator, those CMEs are going to be launching more at Earth instead of above or below the equator. So that's one reason. And then as you go through the solar cycle, these things called coronal holes tend to become more prevalent on the declining phase. So when you're kind of right after the peak on the declining phase, you have the combined effect of still quite a bit number of sunspots plus the coronal holes now opening up, which gives you just more activity. You have the combined effect of these high-speed streams of solar wind plus the CMEs.
I'm curious as to why the red auroras aren't more common, given that they use less, they require less energy than the green ones.
Yeah, that's a good question. The red auroras, I would say, are not as common because the density of particles and at those higher altitudes is so low. So if you imagine the auroras coming down from outer space and it's just not interacting with a lot of particles, there's just not a lot of light that's going to be produced. As you go lower in the atmosphere, it's like an exponential increase in density. So if you reach a certain point, even if that particle doesn't have a lot of energy to begin with, it might just deposit right there in that lower layer because that's where the gas is densest.
You mentioned in one of your slides that to take pictures, it's better to have the moon. I'm surprised because I thought the moonlight would drown out the aurora.
Yeah, so I'll go back to that if I can. So yeah, I mean, it's a little bit nuanced, right? I would say that there's never a bad time to see the aurora or to photograph it. If you're trying to do a real-time video, you really want the moon because you're really just, you're at the limit of what cameras can do. I mean, you're at 1/25th of a second. Imagine trying to take a Milky Way photo at 1/25th of a second. No matter what lens or camera you're using, it's just going to be hard, right? So if you have a moon, there's just more ambient light for you to get more light and more exposure. Now, if you're using a longer exposure, you're just doing regular photography. I personally like having no moon, so a new moon for that. Because people, this is all personal preference, but whenever I show people photos, I wonder if I have any here in this show and tell. These might all be new moon, but whenever I show people photos of the aurora with a full moon, they always say, "Oh, why was it taken during the daytime?" Or when they see the moon, and my mom has said this to me so many times, she's like, "Oh, how is the sun up at night?" And I'm like, "No, that is just the moon." People just get confused, and when you have a new moon, you can actually see the aurora and the light from the aurora showing on the ground, and it turns the ground or the snow green. I think that's really cool. Whereas when you have a full moon, that just doesn't happen because the moon is too bright, unless you have a really, really powerful aurora. So I would say, yeah, if you're just trying to do regular photography, come during a new moon. If you want to just do smartphone photography or real-time video, or you just want to care about the viewing experience, then come during any time or maybe a full moon.
All right. Well, thank you, Vincent, for joining us here tonight.
Thank you.
We really enjoyed your time with us, and awesome presentation. I really enjoyed it. So anyway,